Charles Roeder. I'm going to be talking to you this morning about seismic design and behavior of steel moment frames. In this seminar we're going to be talking about today, it's going to be broken into three parts, as noted before. First part, I'm going to talk about the more or less the history of moment frames and why we are where we are today, because I think you'll find that history is the total reason our provisions are the way they are today. When you do seismic design in the United States, really we're designing for a relatively small force, but we really are designing for ductility, and to assure ductility in that we can actually get the structure to hold together with this small seismic design force, we have the AISC 341 provisions. These provisions are almost totally capacity-based design provisions. So in the first part of the session, I'm going to be talking about the history of why we are the way we are today. The second part, I'm going to be talking largely about the AISC 341 provisions. The third part of the session, I'm proposing to talk about the 358 provisions. Because of events that have happened in the recent past, today we have a special standard for connections of steel moment frames, and that is the AISC Standard 358. And in that third part of the session, I propose to talk about that particular document, and time permitting, we're hoping to do a very quick run through of some sample type of calculations that one may do for a particular type of steel moment frames. Well, with our seismic design today, as I pointed out, we really are designing for a relatively small force. We're relying on inelastic behavior to get us through these really, really big earthquakes. We reduce the force. Most people, when they do seismic design today, still use the equivalent lateral force method. And with the equivalent lateral force method, we have a response modification factor, an R factor, which we use to reduce the forces from what the earthquake would like to deliver to our structure to what we are actually designing for. And then when we use 341 and 358 to make sure that our structure has the inelastic behavior to do this. And so it's sort of a balanced design that we're dealing here. And we have these different provisions to account for this. The basic seismic design forces are really established today in ASCE 7 provision. This is the ASCE 7 2016 document, which is what we'll be using. The 2022 document will be coming out shortly and will be slightly different, but I think you'll find that most of what we say here, it will be valid in that upcoming document. If you look at the document, the ASCE 7-16, one of the key items that we have is this table in ASCE 7-16 defining the R values for the system. This table is quite important because it defines when you can use the equivalent lateral force method and the tools for using it. I think if you look in the table, you'll find that, first of all, there's a reference showing portions of ASCE 7 that might specifically address this variation. But I think you'll see that there are a number of different options for steel moment frames. I think in the slide I have brace frame options, but these are moment frame options. And each of these moment frame options have different R values. They also have a different C sub D value and an overstrength value. The C sub D and overstrength are important in the actual design criteria. But in the far right, you'll see that there are limitations on the height that we can use the equivalent lateral force method. And this is based upon the seismic design group, which is really based upon the seismic response spectra for the region you're designing the structure for, the soil type, and the importance factor of the building. And what you will see there is that I think that some of the systems can be used without limit in the steel moment frames for the special moment resisting frame option. But others have limits or may not even be permitted for certain types of applications. If you're in zone A, B, and C, this might place you more likely to be in less seismically active zones of the United States, in the East and perhaps Midwest. And if you're on the West Coast, you're almost certainly going to be in zone D, E, and F because of the higher seismic response spectra value that you'll be using. And you'll find that in many of these options are not even permitted in that range, or they're severely limited. almost everything has a height limitation under some circumstances. So anyway, this defines the general applications of what we want to do, and this is really the extent of what AISCE 7 deals with for the design of steel moment frames.